So number 65 reads, which one of the following drugs is amphoteric? Which one of the following drugs is amphoteric? Amoxicillin, choice A, choice B, erythromycin, choice C, ciprofloxacin, and choice D, sulfanilamide. So which of the following drugs is amphoteric? Amphoteric drugs. Among the four. Anyone. We skip that one. That one is beyond our scope of practice. Then we can come back to it later. Number 66. All of the following are indicators used for reactions with acidic range endpoint. All of the following are indicators used for reactions with an acidic range endpoint, except. So, which among the following is not an indicator that is used for a reaction that has an acidic range endpoint? Number 66, adio hatujui. Number 66. Shrina, you're saying it's phenolphthalein. I can see you are moving the cursor around that one.
Yeah, I think phenolphthalein is more of the one that tests for bases. I'm not sure, but I was assuming the titration we do it in school using the sodium hydroxide, which is a base. So because of that, it is used for, it has a basic range. Somebody can correct me. I don't know if that makes sense.
Okay. So one of us is suggesting that phenolphthalein, because it's typically used for basic reaction endpoints. Black Panther is thinking that it's more of neutralization reactions. Or can someone just do a search real quick, or indicators used for acidic and indicators used for basic endpoints? So acidic endpoints, as written by DA, we have methyl yellow, methyl orange, bromphenol blue. All of those are for acidic endpoints according to Google.
I've shared a picture on the group.
Yeah, so 7 na kuendelea, we have phenolphthalein pale, we have thiophthalate, and we have alizarin yellow. Those are for the basic reactions to detect the endpoints. We have the phenolphthalein, we have thiophthalate, I don't know, I can't say thio something, but it's related to phenolphthalein, alizarin yellow, and also phenol red. You can see it's extended past the pH of 7, and also a bit of bromothiamol blue. Just it's possible, but they are the center. And another one is thymol blue. So thymol blue, phenolphthalein, and alizarin yellow. Right, those ones are for basic. Then the other ones, the methyl yellow, bromphenol blue, methyl orange, bromocrystal green. I think it's easier to remember the ones for the basic reactions. Then the acidic, you'll do elimination. So phenolphthalein and that related moiety, thiophthalate, alizarin yellow, thymol blue, phenol red, chiastic, and bromothiamol blue. Yeah. So there it's phenolphthalein, and we've seen the other indicators used for the endpoints for basic reactions. Right. Moving on to number 67. The question asks, which of the following principal salts is used in buffer mixtures? So which of the following salts is used in buffer mixtures? Which is the most common type of salt used in buffer mixtures? Is it chlorides? Is it phosphates? Is it sulfates? Or is it bromates? Which one of the following principal salts is primarily, or it's used in buffer mixtures? Chlorides, phosphates, sulfates, bromates.
It should be phosphates because for buffer we use weak acid and the conjugate base. And the chlorides, phosphates, and bromates are all salts of strong acid. So phosphate would be, I think phosphate would be the right answer here.
So phosphates. Anyone else with an different opinion? So phosphates it is, right? Commonly used in buffer solutions, right? Shrina, previously, have we looked at the, I know this is not chemistry, but have we looked at the buffer systems of the body?
I don't think.
You don't think so? Okay. Then can we have someone real quick just take us through any buffer system they know? Because in the body, we know we have buffer systems. Any buffer system you may know, you can just unmute or write on the chat box. We'll read out what you've written. The buffer systems of the body. Buffer systems of the body. Any, you don't have to describe all of them, just the one you know.
Okay, so
Which
this is the phosphate buffer system, which is the most common, and it's in the ECF and the blood and the plasma, and then there is phosphate buffer system is just in the ECF, and then there is the protein buffer system, which is now that's the most abundant in the ECF and the plasma. So this one includes like proteins like albumin. And then there is the carbonic acid, bicarbonate buffer system in the extracellular cellular matrix and the intracellular. Yeah.
Nice, nice. Thank you so much. Thank you so much. Anyone else with something to add on the buffers? So there are the phosphate, the bicarbonate, the protein, right? Protein buffer through the quinoalbumins. I guess no one has something to add on the buffer systems. Next, we go to the next question. All of the following organic compounds can form complexes by chelation with metals, except all of the following organic compounds can form complexes with metals by chelation, except. So which one cannot form a complex? All of the following organic compounds can form complexes by chelation with metals. Which one cannot? Which one cannot? Leo mmenyamaza sana ama mmenyeshewa? Which one cannot? Ama we skip?
I think somebody needs to take us through these things because not all of us are good with chemistry. So yeah.
Pardon, Shreya, I didn't catch you.
Not all of us are good in chemistry. So those who are good can take us through.
Hey, yeah. Me, I'm just good in
What's that
talking.
quiet with chemistry?
Think they've said they are pharmacists, they are not chemists, so they are not good in chemistry. We can skip. Going to number 69, question asking, which one of the following organic functional group has the highest hydrogen bonding potential? Which one of the following organic functional groups has the highest hydrogen bonding potential? So based on the structures displayed, which group will have the highest potential, or rather the highest hydrogen bonding potential?
I think B, because it has 2 hydrogen molecules compared to every other molecule. None of them seem to have hydrogen.
So choose B. Anyone else the different opinion? But
I'm not too sure.
Mm-hmm.
But just a confirmation. The hydrogen bond forms like with the lone pairs, right? For
Yeah,
example,
yeah.
okay. So then even like C, because C would have two lone pairs, like on the oxygen, then it can also form hydrogen bonds. I'm not too sure.
Choose.
Like if
Okay.
we're looking at B and C,
Uh-huh.
why wouldn't it not be C?
I think what I remember when we were studying hydrogen bonds is that the more electronegative an atom or the compound, the higher the potential for hydrogen bonding. So also I was just looking at the structures, and based on that, I think oxygen is more electronegative than the nitrogen, but
Yeah.
I'm just thinking, yeah, I'm not sure. We have, I think Samiha is here, and Samiha was always an organic chem guru. You know, if she's we have Dr. Sonia. Sonia, tell us. Hydrogen bonding between the compounds or among the compounds. There's been between choice B and choice C. Those are the chosen ones. What's your opinion? Which one has the highest potential for hydrogen bonding? Watu wa chemistry wasaidie, watu wa chemistry. I hope no one is keeping quiet with the correct answer. That can be very wrong. Even if you have an opinion, you can voice it. We've not said C is the answer or B is the answer. We've just voiced our opinions. So that we can move, and Shrina number 69, we can also make it red because, yeah, because it's been two differing answers. And to the next question, all of the following are antisense agents except. All of the following are antisense agents except. I can see there's some discussions on the chat. One is asking about oxygen being highly electronegative. Black Panther is saying that anything with a double bond should be out because it is saturated. It is unsaturated, I think. Yeah, it is unsaturated.
So that means that if any compound that has a double bond with these oxygen or nitrogen, that means it can't form any hydrogen bonds.
I think we can take a screenshot, send it to the group, let people discuss it there in the group. Because then someone will find hopefully someone will share a definite answer. Maybe it's somewhere on the internet. Yeah, otherwise we can move on at the time. I'll share the screenshot to the group.
Okay, then we can go to the next question.
Yeah, so all of the following are antisense agents except. All of the following are antisense agents except. So which one is not an antisense agent?
What is the meaning of antisense?
My assumption is perhaps something that works on the level of DNA. I don't know. I don't know. Culprit is showing vasopressin. Perhaps culprit, you can enlighten us. What are antisense agents now that you've chosen vasopressin as the answer?
I think antisense, they're this synthetic compounds. Yeah. I think they're synthetic. So like these other ones are synthetic, but vasopressin is not synthetic.
Yeah, the definition I found, it says it's a short synthetic single-stranded oligodeoxynucleotides that can alter DNA and reduce, restore, or modify protein expression through several mechanisms.
Okay. Yeah, I think based on that, and even Nugal has simplified it further in saying simply antisense agents are drugs that can or do interfere with expression of certain genes, right? They bind to the messenger RNA to reduce the amount of pathogenic proteins. So in short, antisense agents will interfere with expression of specific genes, and vasopressin does not. All the others, their mechanism of action involves some genomic action, but for vasopressin, there is no genomic action involved. So moving on to the next question. She's asking, which of the following drugs is metabolized by N-oxidation? Which one of the following drugs is metabolized by N-oxidation? Is it amphetamine? Is it codeine, imipramine, or mephentamine? Which drug is metabolized by N-oxidation? Daktari is saying choice 71 is imipramine.
I don't know which lecturer, but one of the lecturers in USIU had shared simplified table of these drugs that can be metabolized by different reactions. If somebody has, they can please share. But I also think the answer is imipramine, because oxidation by this compound basically involves it has a nitrogen group, something like that. I don't remember even, but I think B.
Okay. Yeah, so imipramine, we're all in agreement on that question. And if someone has a nice reference, nice photo that summarizes the various drugs and how they're metabolized, kindly share it on the group. Daktari is saying N-oxidation is a type of oxidative metabolism that occurs in the liver and other tissues. It involves the addition of an oxygen atom to a nitrogen atom in a molecule, forming an N-oxide. Many drugs are metabolized by N-oxidation, including imipramine, clonidine, and cimetidine. So simply put, N-oxidation involves addition of an oxygen atom to a nitrogen atom, hence leading to formation of an N-oxide. Also, there's been an image sent on the chat box. We request that while you send an image on the chat box, please also send it on the group so that the reference can be there for those who are not present. But just to read out what is that image. Second, while it opens. The types of oxidation reactions involved in drug metabolism. We have the aliphatic and aromatic hydroxylation for drugs such as ibuprofen. Demethylation, N-demethylation, we have morphine. O-demethylation, codeine. Epoxidation, we have carbamazepine. N-oxidation, we have morphine. S-oxidation, sulindac, deamination, amphetamine. Okay. Moving on to the next question, which asks that all of the following are non-benzodiazepine sedative hypnotics except. All of the following are non-benzodiazepine sedative hypnotics. So which one is not a non-benzodiazepine sedative hypnotic? It is zolpidem, fluvoxamine, zaleplon, or ramiltion. Non-benzodiazepine sedative hypnotics. Brenda is saying choice B, fluvoxamine is not a non-benzodiazepine sedative hypnotic. All the others are non-benzos sedative hypnotics. Now, what are these drugs used for? Majorly, the zolpidem, zaleplon, ramiltion, or what's the pharmacological indication of these drugs? And then what is fluvoxamine, and what's also its pharmacological indication while we're at it? Everyone is shouting on the chat box, insomnia, insomnia, insomnia. Yeah. What about fluvoxamine? Liz is talking about, it can be used for the treatment of obsessive compulsive disorder. Yeah. Moving on to number 73. The question asks, angiotensin 2 formation results in all of the following except angiotensin 2 formation results in all of the following except. So what does angiotensin 2 do and what does it not do? Number 1, regulation of hepatic function. Number 2, hypertrophy and remodeling of vascular and cardiac cells. Number 3, regulation of renal function. And number 4, increased peripheral resistance. I think we've discussed the RAS system time and time again. So all the following are actions of angiotensin 2 except. Black Panther is saying regulation of hepatic function is not associated with angiotensin 2. It does not regulate hepatic function. But all the others, hypertrophy and remodeling of vascular and cardiac cells, regulation of the renal function, increased peripheral resistance, angiotensin 2 leads to all that. Number 74, question asks, which one of the following anti-hyperlipoproteinemias, right, is an HMG-CoA reductase inhibitor? So which of the following anti-hyperlipidemic agents is a HMG-CoA reductase inhibitor? Is it atorvastatin? Hirala said it is atorvastatin. Then what's the classification of cholestyramine? What's the classification of ezetimibe? Wait, there was a day we discussed this in detail, the anti-lipidemic agents. So yeah, so but we won't spend much time there. Moving on to the next question, number 75. All of the following are antimetabolites useful as anti-cancer agents, except antimetabolites useful as anti-cancer agents. So which among the choices given is not an antimetabolite? Black Panther and Spider-Man, they're saying choice C, pentostatin is not an antimetabolite. Anyone with a different opinion? Personally, I thought it's doxorubicin. Is doxorubicin an antimetabolite? Yeah, I'm supporting Kemunto. I thought it's doxorubicin.
Yeah, it is doxorubicin. Doxorubicin is a anthracycline.
Yeah, an anthracycline. And I think it's also an antibiotic. So Stanley has sent something really nice that summarizes the anti-cancer agents. We have, I'll just read it out real quick, just based off that image that has been sent on the group. That number 1, we have the alkylating agents. And in the alkylating agents here, we have the likes of the platinum compounds, carboplatin, cisplatin. We have the nitrosoureas like camustin, lomustine, and streptozocin. We have the nitrogen masters such as cyclophosphamide, ifosfamide, chlorambucil. And we have the triazines such as dacarbazine, temozolomide, and procarbazine. So these are the alkylating agents. The platinum compounds, the nitrosoureas, the nitrogen mustard, and the triazines. Yeah, those are the alkylating agents. Next classification, we have the anti-tumor antibiotics. The anti-tumor antibiotics, here we have our anthracyclines, the likes of doxorubicin, donorubicin, epirubicin. They have that, the anthracyclines have that suffix rubicin. The other class is the non-anthracyclines, such as bleomycin, dactinomycin, mitomycin C, and metoxantrone. Those are the anti-tumor antibiotics, the anthracyclines, and the non-anthracyclines, which are bleomycin, dactinomycin, mitomycin C, and metoxantrone. Moving on to the antimetabolites here, now is where we have the purine and the pyrimidine analogs, or antagonists rather. The pyrimidine antagonists, we have the likes of fluorouracil, capecitabine, and floxuridine. The purine antagonists, we have 6-mercaptopurine and thioguanine. Antifolates, methotrexate, permetrexate, and enzyme inhibitors, still under antimetabolites, we have the likes of cytarabine, gemcitabine, fludarabine. Yeah. Finally, we have the mitotic, not finally. Second last, we have the mitotic inhibitors. Remember the taxanes and the vinca alkaloids, the taxanes and the vinca alkaloids. And we recently differentiated between the two, saying taxanes, they stabilize the microtubules, while vinca alkaloids, they destabilize it. Taxanes, we have like the likes of paclitaxel, vinca, vincristine, vinblastine. Finally, the topoisomerase inhibitors, where we have likes of topoisomerase 1 inhibitors, topotecan and irinotecan. And then the topoisomerase 2 inhibitors, we have etoposide and teniposide. So that's a diagram, is a very nice summary, and even their mechanisms of action are at the top there. Yeah, so you can go through that on your free time. So for this question, doxorubicin we've seen is an anthracycline, an anti-tumor antibiotic. It is not an antimetabolite. Moving on to number 76. Question asks that in zero order reaction, the rate is dash. In zero order reactions, the rate is dash. Number 1, dependent on the intensity of incident light. Number 2, dependent on the concentration of the products. Number 3, independent on the concentration of the reactants. And number 4, independent of temperature. So in zero order reaction, the rate is what? Is it dependent on the intensity of incident light, on the concentration of products? Is it independent on the concentration of the reactors, or independent of the temperature? Zero order reactions. Really saying that in zero order reactions, the rate is independent on the concentration of reactants. On this note, maybe you can tell us, what about first order reactions? So here is zero order. What about first order?
In first order, as the concentration increases, then the rate of reaction also increases by a factor of 2. So it doubles.
Nice. Yeah, when you double the concentration of the reactants, you also double the products, right? Change in Black Panther is also saying that the change in concentration of the reactants affect the reaction rate. Spider-Man is also saying that the first order is dependent on the concentration, in that the rate of the reaction will be doubled if the concentration is increased, right? So in zero order, we've seen it's not dependent. In zero order, we just need the presence of the reactants. However much they are, however little they are, they have no impact on the rate of the reaction. But in first order, or if you double the concentration of the reactants, you double the rate at which the concentration, the reaction will occur. Spider-Man is requesting Hiral to explain for second order reactions. The fake Spider-Man has precisely asked for Hiral.
Okay, so for second order, when you double the concentration, then the rate of reaction will increase times 4. Is that, I think that's all I can say about that. For second order.
Spider-Man, are you satisfied? If you double the concentration, you quadruple the rate of the reaction. If you said, okay, thanks. You're such an ungrateful person. Now we're going with choice C, 76 choice C. Going to number 77, accelerated stability studies. Accelerated stability studies are conducted at what temperature? I think we're all in agreement with the answer that has been highlighted, that they are conducted at 40 degrees Celsius. Nice. Abdul Malik has added on the chat box that examples of major drugs or major examples of drugs that undergo zero order metabolism. We have the likes of phenytoin, aspirin, and alcohol. Those are examples of drugs that undergo zero order metabolism. Phenytoin, aspirin, and alcohol. Yeah, thank you for the addition. Because most drugs will be metabolized through the first order reaction. So it's only a few that undergo this zero order reaction. Number 77, are we in agreement that accelerated stability studies are conducted at 40 degrees Celsius? Yes. I am moving on to, unless someone has something to add on that. You have something on accelerated stability studies, if you really want to add. Go to number 78, which asks, which one of the following is a physicochemical incompatibility? Which one of the following is a physicochemical? Before we go to number 78, Rami is taking us back to number 75. Just a second. Let's see what number 75 has now that we've not gone so far. (75) RH. Did you mean 75 or the one about the
I
hydrogen?
think it's for the one about, no, I think it's for that one, your accelerated studies. The temperature is 40 degrees at what is it called? Relative humidity, 75% for 6 months.
Relative humidity, 75%.
75% for 6 months.
Oh, for 6 months. Hey, you guys understand each other. I envy that. 75% relative humidity for 6 months. Thank you for the addition. So accelerated stability studies are conducted at 40 degrees Celsius at 75% relative humidity for a period of 6 months. Moving on to number 78, which one of the following is a physicochemical incompatibility? Which one of the following is a physicochemical incompatibility? Is it A, potentiation of the therapeutic effects of the ingredients? Is it B, occurrence of a toxic manifestation within the patient? C, destruction of the effectiveness of one or more of the ingredients? Or D, a visible, recognizable change due to interaction between ingredients? What, based on the statements, what is a physical chemical incompatibility? Physical, meaning you can see; chemical, meaning there's a reaction; incompatibility, meaning they cannot stay together. Black Panther saying that choice D, that is an example of a physical chemical incompatibility. Comfort is also backing that answer. Evayani also backing that answer, that a recognizable change due to an interaction between the ingredients is an example of a physical chemical instability. Rami is kindly requesting that we remind ourselves on incompatibilities. We remind ourselves on incompatibilities. Anyone who is willing to remind us of the various incompatibilities? Helen Kerubo. It has been sent to the group. We just see it. Stanley, just to read out what he said, the types of drug incompatibility. Number one, we have therapeutic incompatibility, whereby we have modification of the therapeutic effect of one drug by the prior concomitant administration of another. That is an example of a therapeutic incompatibility, whereby there's been a modification of the therapeutic effect of one drug due to the administration, simultaneous administration of another drug, essentially drug-drug interactions. Going to the physical incompatibility, this is whereby there is an interaction between two or more substances which lead to either a change in color, a change in odor, taste, viscosity, or morphology. Right? Physical incompatibility is an interaction between two or more substances which lead to a change in color, odor, taste, viscosity, or morphology. Right? Another term given for this is pharmaceutical incompatibilities. Finally, the third one on the photo is the chemical incompatibility, whereby, simply put, there's a reaction between two or more substances which will lead to a change in the chemical properties of a pharmaceutical dosage form. Right? There's a chemical interaction between two or more substances which will lead to that change, which will lead to the change in the chemical properties of a pharmaceutical dosage form. So we have the therapeutic incompatibility, physical incompatibility, and chemical incompatibility. So from the explanation given, Black Panther is telling us that choice A will be an example of a therapeutic incompatibility, right? Because in the therapeutic incompatibility, we've seen that what is happening is that there's a modification of the therapeutic effect of one drug when it's co-administered with another drug.
I think the above three are all therapeutic incompatibility. B is a chemical occurrence of a toxic manifestation within the patient. And what about C?
How is B chemical? Occurrence of a toxic manifestation within the patient. So after the patient has taken it. How is that chemical? Just asking for clarity. I also think they are all therapeutic. Anyway, we've seen the various types of incompatibilities: therapeutic, chemical, and physical. Yeah. Moving on to number 79, the question asks, which of the following drugs does not? Which of the following drugs does not undergo hydrolysis? Is it cocaine? Is it procaine? Is it benzyl penicillin? Or is it salicylic acid? One of the following drugs does not undergo hydrolysis: cocaine, procaine, benzyl penicillin, or salicylic acid. Bansri is saying that the answer should be D, because salicylic acid is a product of hydrolysis. Anyone with a different view? So the following drugs does not undergo hydrolysis. So if silence, I'm assuming we're all agreeing that that the answer is salicylic acid, right? Black Panthers say that benzyl penicillin, that is PENG, it undergoes hydrolysis in the stomach, hence the reason why it is given through the IM route or route. Then on this, have we discussed just local anesthetics before, the esters and the amides? Was here procaine, cocaine, esters, and then there are the amides like lidocaine. I don't know if that has been discussed before. The local anesthetics, local anesthesia. There's a request that we go through both local anesthesia and general anesthesia. Go through local anesthesia and general anesthesia. Volunteers. Local anesthesia, general anesthesia. Which one do you know? Which one are you more conversant in?
Okay, so for the local anesthesias, they're classified into three. There's the injectable ones, which are further classified into low potency, such as procaine, intermediate, such as lidocaine, and high potency, such as tetracaine. Yeah, those are the injectable ones. Then you have surface. So that's like if they're soluble or insoluble. So soluble ones would be like cocaine, lidocaine. Then insoluble ones would be like benzocaine. Then according to their linkage, for amide linkage, there would be lidocaine, bupivacaine, prelocaine, and the ester linked ones would be cocaine, procaine, tetracaine. And one way to remember which one has the amide linkage, just remember, like, for example, if it's lidocaine, it has an I at the start. Then there's bupivacaine also, it also has that bupi, like that I. Then there's also prelocaine, which has that I again. Those are all amide linked. For ester ones like cocaine, they don't have an I at the start. It's only in the cane. So I think that's something to remember. Yeah, those are the local anesthetics. I don't know. I'm not too sure about the general ones. I just know there's IV agents and inhalational ones. Not sure about the classification.
Thank you so much, Hiram. Thank you so much. I think Dr. Karimi had a very nice summary of general anesthesia or anesthetics in a previous discussion. Don't know if she's around to just give a quick summary.
Okay, what with the general anesthesia, we have the intravenous and inhalational, whereby the intravenous are more used for induction, things like diopento, entomidate, propofol. And then the maintenance, we use things like allothine, enflurane, sevoflurane, and the rest. But it is all, remember, in anesthesia, we don't have a certain dose, especially for inhalational, so we only check on the response of the patient. Yeah, and some are greater advantages than the others. For example, if you're using something like allothine, you should be aware of some side effects such as hypothermia, and also some have mean alveolar concentration, which is low. When it has a low mean alveolar concentration, it means it is a nice anesthesia or anesthetic, sorry. But all this is more dependent. You cannot get one certain anesthetic agent which will qualify to have all of them. So it all depends. Some are good in one area while others are not. So we have inhalational and intravenous. Intravenous usually for induction and inhalational for maintenance. Thank you.
Thank you so much. Thank you so much, Doc. Anyone with something to add on what Dr. Hiral and Karimi has said?
Just to add on that, for inhalational agents, the higher the minimum alveolar concentration, the lower the potency. And if the blood gas partition coefficient is high, then that determines the onset of action. So if it's high, then it will have a slow onset of action because it will be more dissolved in the blood instead of now in the gas. So yeah, I think something like that. But I just know that if the blood gas partition coefficient is high, then it will have a slower onset of action. So just to repeat that again, if high minimum alveolar concentration, low potency, high blood gas partition coefficient, slower onset of action. Yeah.
Also, a
Thank
little addition.
you.
Thank you so much. Also, a little addition, like before anesthesia, remember we also have pre-anesthetic medications, which whereby they are helping us to prepare the patient for anesthesia. That's general anesthesia, something to drugs to reduce anxiety, such as benzodiazepines. We can also use some drugs to reduce secretions and vagal bradycardia. That's why we use something like because we don't want this patient to have excessive anti-muscarinic effect. We will give things like atropine. Then we can also manage this patient against messes. Messes can be prior and post. So we can give things like metoclopramide and yes, such, and also we can you can get a condition which needs urgent surgery. So you can also hasten gastric emptying before emergency surgery. That's why you use things like domperidone. Thank you.
Thank you so much. Thank you so much. Anyone else with anything to add on anesthesia as a whole, local, general, pre-anesthetic medications? Anything in the line of anesthesia?
Yeah, an example of the one that has a higher blood gas coefficient is halothane, and the one that has a lower blood to gas coefficient is nitrous oxide.
Nice, nice.
Also, to take you back a little on local anesthetics, I remember we said that they usually do the blockade of transmission of an impasse. So they have first to enter the cell. So for them to enter the cell, they should not be ionized. Then after entering the cell, they have to change again so that they don't leave the cell. So they have to have a pKa or almost near to the body pH so that they are not completely ionized. But you find that there was you could be having something like a suppurative wound. And remember, in this environment, the pH is around 5.5, not 7.4. So some of them will not work properly here. But a drug like mepivacaine for local, won't be active in this sense. So the pH, the pKa of a drug usually is very, very crucial when it comes to local anesthetics.
Nice. So the pKa.
Can you repeat that, please?
Okay, I will say that for the local anesthetics, for them to be effective, the pKa should be almost towards the same range with the pH of the blood. Remember, there is a correlation between the pKa and the pH. So if they have, they will be ionized easily, they will not elicit the effect. They will not give us the proper anesthetic effect if it's local. So they should first enter the cell. Then when they have entered to block, they should not also leave the cell because we want the activity to remain for some time. So their pKa should be within the pH of the body system. But for some cases where you have a wound or like an area which has an infection leading to acidic condition due to a wound, means the pH would be around 5.5, not the 7.4 of the body. Some of the local anesthetics would not work, but there are some which are good at that. An example is mepivacaine.
Nice, nice. I believe yeah, even Hiral has written on the chat box about what she was explaining. When it has a high minimum alveolar concentration, it has a low potency. And if it has a high blood gas partition coefficient, it will have a slow onset of action. As something that our lecturer told us, something to remember anesthesia by, that is a general anesthesia. Whatever is happening in the lungs is what is happening in the brain. Whatever is happening in the lungs is what is happening in the brain. So if a drug needs to have a high concentration in the alveoli, it means it also needs to have a high concentration in the brain. That means it has a low potency, right? So that was a trick. If someone can, yeah, Brenda is adding that ketamine is known to cause dissociative amnesia. Dissociative amnesia, right? Dissociative amnesia. Again, I send you to the USIU people to explain to you the word dissociative. We can move to number.
I wanted to add on the pre-anesthetics. We should also give them antihistamines just to avoid any allergic reactions like diphenhydramine and opioids just for pain.
Yeah. Antihistamines to avoid any allergic reactions. Yeah. Opioids for pain. Yeah. And between the esters and the amides for local anesthetics or anesthesia, which one is more likely to cause allergic reactions? Between the esters and the amides.
I think the amide, but I'm not too sure.
Nice. Yeah. The
Or is
amides,
it-
they are less likely. Yeah, you're right. They are less likely to cause allergic reactions as compared to the esters, the likes of procaine, tetracaine. Yeah. And I hope we remember why some of these anesthetics can be co-administered with norepinephrine, or they are found even in combination with norepinephrine, right? Stanley, do you want to tell us why? Why can you find a local anesthetic co-administered with norepinephrine?
Hiyo sijui, hiyo imenipita.
Nitroin. Kimunto was told
One is to make the surgical and ina facilitate nini ina reduce to your bleeding.
Nice. You have to prolong the action. If we are vasoconstricting the vessels, it means that drug is not living there, right? So prolongs the duration of action of the anesthetic. And of course, there are periods when you can use with noradrenaline, there are periods you should not use with noradrenaline because of the risk of necrosis. It all matters with the capillaries around the area of which you are injecting. Going to number 80, which of the following factors is not a component of the Arrhenius equation? I think the fake Spider-Man really went ahead of us and even tweeted the Arrhenius equation and told us that the answer is C, right? And even sent an image of the Arrhenius equation, K is equals to A to the, I don't know how to say that, E negative activation energy over RT. I think R is a constant, T is temperature in kelvins, right? So absolute temperature is there in T, the gas constant R, energy of activation EA, pH is not there, right? I think that one is straightforward, but how was Arrhenius equation being applied in chemistry? What was the significance of Arrhenius equation, or rather, in what topic or topics did we talk about the Arrhenius equation. Watu wa chemistry, Dr. Sonia, you're too silent. You're too silent. Mystique, Coach, Samsung, SMP 619. No comment, Dr. No comments. Arrhenius equation. Anyone? Where did we see the Arrhenius equation? Chemistry wamesema it's not their forte. Someone is saying that it can be used to determine reaction rates. We move to number 81.
It's used to determine the effect of temperature on the rate constant and the rate of reaction. So for example, if the rate constant, that is K, is going to double, then the rate of reaction will also double.
Nice. So basically, it's used to determine the effect of temperature on the rate of the reaction.
Yeah, and catalysts on the activation energy.
And catalyst on the activation energy. Yeah, nice.
Yeah, like when you add a catalyst, then you decrease the activation energy, increasing the rate of the reaction. Yeah. If the activation energy is decreased, the rate of reaction is increased.
Could you please repeat?
When you add a catalyst, the activation energy is decreased. K is also increased, and the rate of the reaction is also increased. Same with temperature. And also, if you increase the concentration of the reactants, if it's not zero order, that is, then the K is not affected, but the R will increase. That's the rate.
Thank you.
Nice, nice. So the Arrhenius equation, yeah. Moving on to number 81, which one of the following reactions represent alpha radioactive decay? Which one of the following reactions represent an alpha radioactive decay? So we're expecting to see Spider-Man say that the answer is choice C, whereby we've emitted a helium particle 4-2, right? So what are the other types of radioactive decay, and what do we expect? We've seen alpha with beta, gamma, positron, right? So what do we like in alpha radioactive decay? We see we emit a helium particle. What about in the others? What about in beta? What about in gamma? What about in positron? And any other that I may not have mentioned. Just quickly, the types of radioactive decay. Types of radioactive decay. Amashrina, you can help us there.
Okay, so for the beta decay, what do you say? The electron, like think choice B is a beta decay. I don't know how to explain.
So for the beta, the decay series, it's a 0 and -1, and for the gamma it's 0, 0.
Nice. Yeah. Also, a photo has been sent on the group. On the alpha, beta is at 0 on top, -1 hapo chini. Gamma is at 0, 0. There's just emission. The energy is emitted. Then there's also the positron. I think that's the positron. It's 0, 1, right? And now for the positron, is just the opposite of the electron or the beta decay. Finally, we have the electron capture, which is now the electron 0 - 1 is written on the reactant side. That's why it's called electron capture. It's been captured so that we can form a new product, a new atom, a different nuclei, right? Then just as a reminder that the mass number is written on the top, the atomic number hapo chini. Mass number is A, atomic number is Z. Yeah, I think we saw a question that tested on that. Moving on to the next question. The Kern-Ingold-Prelog convention used to describe configuration about a chiral center uses what symbols? The Kern-Ingold-Prelog convention used to describe configuration about a chiral center uses what symbols? Is it D and L? Is it R and S? Is it Z and E? Is it plus, minus? The Kern-Ingold-Prelog convention system used to describe configuration about a chiral center. So just leave alone the name. Let not the name scare you. Configuration about a chiral center. When we are describing chiral compounds, what's the suffix we put before? Is it D and L? Is it R and S? R and S. Hapo tuko pamoja. R and S. We're good. Someone in the chat box amesema that hapo tuko sawa. At hapo we are sure of 1 mark on next Wednesday, but what? Only 1 mark. Moving on to number 83. Unless someone has something to add on this stereoisomers. We've looked at stereoisomers before, and yeah, I think we are good. Moving on, which one of the following acids give rise to chlorate ion? Which one of the following acids give rise to chlorate ion? Right. So the one with 1 oxygen, 2 oxygen, 3 oxygen, or 4 oxygen? If you tell me it's the one with 3 oxygens, what does Spider-Man nice? What does D give rise to? What will we call D? That HClO4. And what will we call HClO2? What will we call HClO? That's what Spider-Man said for ClO4, that is the perchlorate ion. HClO2 chlorous acid. Is it chlorous or chloride? HClO is the hypochlorous acid. Then just to, someone is taking us back to number 82, that asking what is the Z and D system, or Z and D symbols, what is it used to describe? The Z and E. ZRNS is for the Can Ingold. Z and E, Kemuto has said, is for geometric isomers. Z and E is for geometric isomers. Z and E is for geometric isomers.
Z is cis and E is trans.
Ah, nice. So Z is cis and E is trans. Z is cis and E is trans. So Z trans, Z. Try to make those correlations. What of D and L? D and L. What is D and L describing?
Dextrorotatory and levorotatory.
Dextro and levo rotatory. That's right. Dextro and levo rotatory. So do this dextro, yeah, optical isomers. So dextro will rotate the plane polarization to the right, light to the right, levo to the left. L, levo left, right? Levo left. Number 84, the question asked, so following analytical instruments employs a radio frequency receiver detector. Which one of the following analytical instruments employs a radio frequency receiver detector? Which analytical instrument employs a radio frequency receiver detector? Is it NMR? Is it mass spec? Is it atomic absorption, spectrophotometer, or is it spectrofluorimeter? Which one employs a radio frequency receiver detector? Is it NMR? Is it mass spec, spectro, or atomic absorption spectrophotometer? Which analytical method employs a radio frequency detector? Trina said it is NMR. NMR. When we are at number 84, have we discussed the various instrumental methods of analysis? NMR, IR, and mass spec. I think those are the major ones. And UV spectroscopy previously. Shrina, have we discussed those ones?
I am not sure. I don't think so.
Okay, does anyone want to give a quick summary of any between NMR, mass spec, and IR, and UV spectroscopy? I think those four are the major types that are commonly employed. NMR, IR, UV, and mass spec. Which one do you do? Which one? What does it do? How does it detect? What is the principle of that machine? Such things.
So for NMR, it's the principle behind it is that some nuclei exist in a specific nuclear spin state when exposed to an external magnetic field.
Yeah, so it's about the spin.
Yeah.
Yeah. So what anything unique in NMR maybe that is testable, maybe something that makes NMR stands out? We've highlighted this radio frequency receiver detector. To everyone, by the way, we have 41 of us, and it's the same 5, 6 people talking or writing on the chat box. Please, let's engage. Just write whatever you have. That little you may know is enough, because we are here to learn from one another. If there's no contribution, I guess we'll continue to the next question. Number 85. Which one of the following has the lowest mass? Which one of the following has the lowest mass? Is it the neutrino, the electron, the positron, or the neutron? Which one of the following has the lowest mass? Positron, electron, neutron, or neutrino?
This one should be neutrino because electron and positron have the same mass. It's just the opposite symbol,
Charge.
and neutron is the least.
So we're all in agreement that it is neutrino. Neutrino has the lowest mass. Electron and positron have the same mass. So both of them, we eliminate them. Neutron has a very big mass. We know it contributes to the atomic mass. So number 85, yeah, A for neutrino. Moving on to number 86.
Somebody has a question on the group. I mean on the chat box.
They're asking if spectrophlorimeter comprising, is the spectrophlorimeter the one comprising of a fluorescent lamp? If anyone knows. Spectrophlorimeter. I think we can be moving, Shrina, and we hope someone will respond to the person on the chat box. Because yeah. So number 86 is asking, what is the name of the following chemical? Is it pyridine? Is it pyrimidine? Is it pyrazine, or is it pyridazine? Pyridazine. Name of the following chemical ring system: pyridine, pyrimidine, pyrazine, or pyridazine.
It is B.
So pyridazine, the name of that structure there.
For pyridine, it's just one nitrogen. For pyrimidine, it's 1,3 nitrogen, dinitrogen. Like over here, it's 1,2. For pyrimidine, it's 1,3, and the last one, pyrazine, is 1,4.
So pyridine is 1, pyridazine is 1,2, pyrimidine is 1,3, pyrazine is 1,4.
Yes.
Perfect. Okay. So if someone has that image of common heterocyclic compounds, or those common heterocyclic compounds, you can share on the group. Yeah. Next question. As phenylalanine, also not phenylalanine, phenylethylamine reacts with a carboxylic acid halide to form an isoquinoline through what? Phenylethylamine reacts with a carboxylic acid halide to form an isoquinoline through what type of synthesis or reaction? Scrap, Fischer, aldol, or Fischer-Naprica synthesis? We can move to number 88. The IUPAC name of the following compound. The IUPAC name for the following compound below. So if you draw the compound, so it's a 2-methyl pentane, right? 2-methyl pentane. And next, the question asks, which one of the following someone is saying, talking about number 87, saying that according to Google, Spider-Man, again, please just share the link to the group. It really simplifies things so that everyone can access it when it's in the chat box, it will be lost after the meeting. So according to Google, it's the circle choice that Fishler Napriaski synthesis. Number 89. Which one of the following physical properties is not correct for ethanol? Which one of the following physical properties is not correct for ethanol? The melting point, the boiling point, the density, or the lethal dose? Which one is not correct for ethanol? Black Panther is saying choice A, boiling point. That boiling point is not correct for ethanol. What's the boiling point of ethanol? (78.5 degrees Celsius). 78.5 degrees Celsius. So that 88.5 is not correct, right? Moving on to number 90. Moving on to number 90. Question asks, which of the following forces causes nonpolar molecules to aggregate? Which one of the following forces causes nonpolar molecules to aggregate? Which one of the following forces causes nonpolar molecules to aggregate? Is it ionic interaction, dipole-dipole interaction, van der Waals forces, or hydrogen bonding interaction? So which one would cause nonpolar molecules to aggregate among the choices listed? Black Panther is saying ionic interaction would cause nonpolar molecules to aggregate. Perhaps on that, I have my question is: do nonpolar compounds exhibit ionic interactions? If they are nonpolar, I don't know. I don't know much of chemistry, but maybe someone can explain that. Do nonpolar molecules exhibit? Do they have these ionic charges? With me on this question, I was thinking van der Waals, but now I'm not sure. Just opinion.
I also think van der Waals, because when you say sodium chloride, in itself, that's a polar molecule. Yeah, because that's just common salt, which is easily it easily dissolves in water. So personally, I was also thinking when we talk about hydrogen bonding, so we have the OH, which are present in, even when we say carboxylic acid in itself, it's a non-polar molecule. even though it can be dissolved in. Even though it has the OH, we still consider it a non-polar molecule. So I don't know, one of the two. I'm not sure which.
Nice. Thank you. Anyone else with different opinion? Maybe Black Panther, you can explain maybe to us why ionic was. Like we've explained why we don't think it's ionic. Maybe you can explain why you think it's ionic. Or someone else, maybe someone is thinking hydrogen bonding is the answer also. Anyone? We are on question number 90. On question number 90, we're asking for thoughts. The two answers have been given so far: ionic interactions and van der Waals forces. Chemistry people, you're really letting us down. You're not contributing to the discussions, and we'd move much faster if you did. Mr. Lover, Samsung, again, do Sonia Kosoko, but yeah.
So it's saying the non-polar molecules can aggregate when they have weak hydrogen bonds. So it is van der Waals forces.
Van der Waals forces.
With Shrina, you said, so they wouldn't aggregate if they had strong hydrogen bonds. Back to that question.
Yeah.
From just what you read, because I think if they have strong hydrogen bonds, then also we are saying that they would still aggregate, because see, the hydrogen bonds bring them together. So why isn't the answer
non-polar molecules and okay, like the way guys questioned before, how can it be ionic? Because they are non-polar molecules, and non-polar molecules don't have any ion charges there. So ionic interaction is already out. And what Google is saying is non-polar molecules can aggregate by weak hydrogen bonds, but they don't like it very much, in contrast to much stronger ionic attraction with hydrophilic molecules. So don't know.
so thanks.
I think even perhaps if we just think of something like methane being non-polar, we can also eliminate methane having this hydrogen bonding ionic interactions, dipole interactions. Yeah, even so we can land on van der Waals.
Also, just on that, non-polar molecules are basically bonded by covalent bonds, and under covalent bonds we have dipole and van der Waals forces. So that will eliminate option A and D. Yeah, we're left with two options, B and C. We know dipole interactions are a bit stronger than van der Waals forces. You can correct me if I'm wrong.
No, yeah. It's dipole. We have two poles. Yeah.
So
Yeah.
van der Waals is the weaker one. So the answer is C. So non-polar molecules are also known as covalent bonds. Yeah. And for the aggregation to occur, they should have weak hydrogen bonds. Yes, they prefer weaker hydrogen bonds for aggregation. That is what it means in simple terms. Have you understood?
Yeah, I really have. Thanks.
Thank you. I think we can start from here.
Yeah.